Alright, hello everyone. Welcome to Passionate Minds. My name is Prabhasha, and today I'm going to be teaching to you a bit about SCH3U. And today's lecture is going to be focused on chemical proportions and a little bit of stoichiometry as well at the very end. Alright, so the law of definite proportions states that in compounds, elements are going to be present in the same proportions by mass. So, just to reiterate, this means that for water or H2O, for example, the elements hydrogen and oxygen are going to be present in the same proportions by mass. The presence of hydrogen and oxygen are going to be directly related to the mass of those two elements. Now, the composition of a compound is given normally in percentages by mass for individual elements. And the percentage composition of compounds is the mass of each element found in the compound. So, quick examples just to kind of understand what I was talking about a bit earlier. If we're looking at the percent composition of hydrochloric acid or HCl, with 1 gram of hydrogen reacting with 4 grams of chlorine to form 5.00 grams of HCl, basically just to find the percent composition of each of the two elements present, what we do is we take the mass of hydrogen and then divide it by the total mass of the compound. So 1 divided by 5 and then multiply by 100% will give you 20% hydrogen. So the percent composition of hydrogen in HCl is going to be 20%. For chlorine, since we have 4 grams reacting to form 5, we divide 4 by 5 and multiply by 100%, and we get 80% chlorine for by composition. Now, looking at the second example, if we have 2.00 grams of sodium reacting with 6 grams of fluorine to form 8 grams of sodium fluoride, same thing. We take the mass of sodium divided by the total mass of the compound, multiplied by 100% to get the percent composition of sodium. And to do it for fluorine, the same thing. We take the mass of fluorine divided by the mass of the entire compound, multiplied by 100% to get the percent composition of fluorine, which is 75%. Sodium is going to be 25%. Now, taking a look at the percent composition by chemical formula, this is a little bit more different, as we're going to be taking into account the molar mass of individual elements when finding the percent compositions by the chemical formula. A quick example of this is when looking at the percent composition of hydrochloric acid, or HCl. So, we know the molar mass of hydrogen to be 1.01 grams per mole, or big M, and we know the molar mass of chlorine is going to be 35.5 M. So the percent composition of hydrogen in this compound is going to be 1.01, the molar mass of hydrogen, divided by the molar mass of the entire compound, which is going to be 35.46, divided by multiplied by 100% to give us 2.77%. So this is a percent composition of hydrogen within this compound. Now to find chlorine, we take its molar mass and divide it by the molar mass of the entire compound. This should be 35, and we get 97.23%, which is going to be the percent composition of chlorine within this compound. And this is only if we're looking at molar mass of the elements. We don't know the masses for this example. Now, empirical formula and molecular formula are two very important terms that you're going to need to know throughout chemistry in high school and university and whatnot. Empirical formulas are the simplest formulas that can express a compound. It's going to show you the lowest whole number ratio of elements within a compound. Empirical formulas are proven and disproven in lab experiments, like trying to understand them, proving them as well is done normally in lab experiments, but we can find the empirical formula with some given information as well. And molecular formulas are just the actual formula of a compound. It'll show you exactly how many atoms of each element are going to be present within that compound. To give you guys some examples to understand the difference between the two, the molecular formula of octane is C8H18. However, the empirical formula, it's the simplest formula. So since they're both divisible by 2, we can reduce this to C4H time. This is the simplest way we can express octane, the empirical formula. Taking a look at benzene, which has a molecular formula of C6H6, its empirical formula is going to be CH because both sixes are divisible by 6 to give you 1. This is why the empirical formula is going to be CH, however, the molecular formula is different. Finally, taking a look at water, the molecular formula of water is H2O. The empirical formula is also going to be H2O because you can't divide 2 and 1 by any number other than 1. So the empirical formula is actually the molecular formula for water. But basically, whatever subscripts you have, you want to reduce them to the lowest possible terms. So if you had 8 and 18, you divide by 2. If you had 10 and 20, you divide by 10. You get 1 here and 2 there, CH2, if it was C10H20 for the molecular formula. Now, determining the empirical formula, we need to determine the number of moles present for each element. This can be done with a given mass and the molar mass, which is already found on the periodic table. So, if the percent composition of elements is already given, but not the mass, we're going to be assuming that the composition of elements, the compound, is going to be 100 grams. We're going to use 100 grams as a constant for that compound. To just explain this a little bit more, if we had 75% composition of magnesium and 25% composition chlorine present, we're going to be assuming that we have 100 gram samples so that we have 75.0 grams of magnesium and 25.0 grams of chlorine. Now, to determine the ratios between moles, we're going to be dividing all the moles by the mole with the smallest value. So, if we have 2 moles of hydrogen, 3 moles of carbon, and 4 moles of oxygen, we're going to be dividing all 3 values by 2, which is because it has the smallest value. And if you get a fractional ratio to determine the ratio, let's say 1.2, 2.3, 3.6, whatever, we're going to be multiplying the ratios by the smallest number. They'll give us all whole numbers. So, for example, if we had 1.2 as a ratio, the closest whole number is going to be 6. So we're going to multiply 1.2 by 5. So the ratio is going to be multiplied by an additional 5 to get to 6. So all 3 ratios will be multiplied by 5. If we're looking at another example, let's say 3.6, the closest to 3.6 would be 18 because 3.6 times 5 is 18. So you'd have to multiply all the ratios to get a ratio of 18, like that. So we can only round numbers if it's between 0.1 or less. So, for example, 1.90 can round up to 2 for the ratio, but 1.7 cannot round up to 2. It would have to round up to, you'd have to multiply to get to about 5.1 where you could round down. But like I said, it's only if it's 0.1 or less, like 1.90, 1.10, 1.09, 1.92, stuff like that. Now, these are some examples that I've created. This first example is right here. It's a little bit different in the form than the other two, and I'll explain that as well as I go along. So, determining the empirical formula of compound with 52.14% carbon, 13.13% hydrogen, and 34.73% oxygen. Always state that we're going to be assuming that there's a 100 gram sample, so your teacher knows that you're assuming this, otherwise it's kind of incorrect. Because of this, we have a mass of 52.14 grams of carbon. We already know the molar mass is 12.0 grams per mole. 13.13 grams for hydrogen, 34.73 for oxygen. We already know the molar masses for these two elements as well. And what we do is we find the moles of the 3 elements. To do this, we take the mass divided by the molar mass, as I've told you in previous lectures, and we get 4.35 moles of carbon, 13.0 moles of hydrogen, and 2.17 moles of oxygen. To do the ratio, again, like I said, we divide all 3 mole values by the smallest number, which is 2.17 moles, and we get a ratio of 1 for oxygen, as the lowest is always going to be 1. Hydrogen here has a ratio of 5.99, which can round up to 6. Carbon has a ratio of 2.00, which rounds 2. Therefore, the compound empirical formula is going to be these three numbers are going to be the subscripts. So you have two atoms of carbon, 6 atoms of hydrogen, 1 atom of oxygen, or C2H6O. This one is a bit more cleaner. Tables are a lot easier to understand these examples than rather than doing it straight down. Determine the empirical formula with a compound with 57.14% carbon, 6.16% hydrogen, 9.52% nitrogen, 27.18% oxygen. I can assume it has 100 grams. Write the masses down for each element. Write the molar masses down for each element. Find the moles by dividing the mass by the molar mass. We get 4.76 for carbon, 6.16 for hydrogen, 0.680 for nitrogen, and 1.70 for oxygen. Find the ratio. This is the lowest one, so we're going to be dividing all 4 of them by 0.68, and we get 1.00 for nitrogen, 2.50 for oxygen, sorry, 8.97 for hydrogen, and 7.00 for carbon. Since we have to multiply this by 2 to get to 5, the closest whole number, we multiply all the ratios by 2 as well to get to the next whole number. So this is going to give you 18 hydrogens, 2 nitrogens, 14 carbons, 5 oxygen. The empirical formula is really big, but it will be C14 H18 N2O5. And again, we multiply these numbers because this ratio is not close to a whole number whatsoever. Multiplying by 2 gives you a whole number. And when you multiply one ratio, you have to multiply all of them as well. Now, taking a look at the final example we have a compound with 38.70% carbon, 9.75% hydrogen, 51.55% oxygen, and we want to find the empirical formula. We're going to assume that we have a 100 gram sample as per the usual, and we write down the masses of the 3 elements here. Write down the molar masses as well. Remember, hydrogen has a molar mass of 1.01. It's common to just write it as 1, but then the numbers aren't going to be as accurate as you'd want them to be. Write down the moles as well. 3.23 moles for carbon, 9.65 moles for hydrogen, 3.22 moles for oxygen. Making the ratio 3.22 is the lowest. We get a 1.00 for oxygen, 1.00 for carbon as well after rounding, and 3.00 for hydrogen. So these have a multiplier of 1 because we don't have to multiply them at all to get a whole number, as they're already whole numbers. Therefore, the empirical formula is going to be CH3O. Alright. Now, how to determine the molecular formula? If you want to find the molecular formula, the molar mass is already going to be given to you for the compound. We're going to be doing the same steps to get the empirical formula as before, and after the empirical formula is obtained, we're going to be calculating the molar mass of the empirical formula. Now, after this step, we divide the molar mass of the compound by the molar mass of the empirical formula. The number obtained here, it should give you a whole number, is what you're going to multiply the empirical formula by to get the molecular formula. So, for example, if you have an empirical formula of CH4O3, and after dividing the molar mass of the compound by the empirical formula, you get 3, the molecular formula is going to be multiplied, is going to be 3 multiplied by the empirical, which is going to give you C3H12O9. And I have some examples just to explain this a little bit better as well. So, compound has 40.0% carbon, 6.70% hydrogen, 53.3% oxygen, and the molar mass is 60 grams per mole. For the this molar mass represents the molecular formula's molar mass. Again, assume it has 100 grams as a sample. We write down the masses as before. The molar masses, to get the moles again, divided by the mass by the molar mass, and we get 3.33 for carbon, 6.63 for hydrogen, 3.33 for oxygen. We're going to divide all 3 by the lowest number, which is 3.33. We get the ratios of 1 for carbon, 1.99 or 2 for hydrogen, and 1.00 for oxygen. So The empirical formula is going to be SCH3U, which has a molar mass of 30.0 grams per mole. Again, we divide the molar mass by the empirical molar mass to give us 2. This 2 means we have to multiply all the subscripts in the empirical formula by 2. Multiply the whole compound by 2 to get the right number of atoms for each element, which means we're going to have C2H4O2 as the molecular formula. Now, a hydrocarbon made up of hydrogen and carbon atoms has a molar mass of 80.0 grams per mole, and it is composed of 85.7% carbon. We're going to assume it has a 100-gram sample, and although we're not given the mass of hydrogen, since it's a hydrocarbon, all hydrocarbons, a hydrocarbon basically means that it's only composed of carbon and hydrogen, in this case at least. Because of this, we just take 100 grams, we subtract that by 85.7 because we already know the percent composition of carbon, and that'll give you the mass or the percent composition of a hydrogen as well within this compound. So we get the masses, we already know the molar masses, divide the mass by the molar mass to get the moles, which is 7.14 for carbon, 14.2 for hydrogen. Find the ratio after dividing both by the smallest number, which is 7.14, and we get 1.00 for carbon, 1.99 for hydrogen, which is basically 2, meaning that the empirical formula is going to be CH2. Now this molar mass is about 14.0 grams per mole. The molar mass of the entire compound is 84.0, so divide this by the empirical one, and we get 6. This 6 means we multiply all the atoms in the empirical formula by 6 to get the molecular formula, meaning that the molecular formula is going to be C6H12. A final example here has 24.8% composition of carbon, 2.00% composition hydrogen, 78.2% composition chlorine with a molar mass of 96.9 grams per mole. Again, we write the 3 masses after assuming that we have a 100-gram sample, write the molar masses, divide the mass by the molar mass to get the moles, and we have 1.98, 2.07, 2.06. The ratios are going to be the ratios are going to be 1.98 divided by the 3 numbers, and we get 1.00 for hydrogen, 1.05 for carbon, which is about 1, and 1.04 for chlorine, which is also about 1. So the molar mass of CHCl is about 48.46 grams per mole. Divide this by the actual molar mass, and we get about ratio 2, meaning that we multiply the empirical formula's atoms by 2, so the molecular formula is going to be C2H2Cl2. Alright. Hydrates. Now, hydrates are a little bit different. They're water compounds that are attached to another compound, typically an ionic compound. They're related to percent compositions and everything we've been talking about before, and I'll go into some examples later on to explain that a bit better. When they are attached to an ionic compound, they're called hydrid ionic compounds. And a good example of this is CuCl2 and 3 hydrates, which is also known as copper 2 chloride trihydrate. This is how you would name this particular compound. This dot right here indicates that there's going to be hydrates present. It's like you're multiplying the compound by hydrates. The prefixes for hydrates are going to be the same as the nonmetals. So we got mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. So example here, aluminum phosphate tetrahydrate. There's 4 waters. This is why we use a prefix tetra. And again, we use that circle symbol, which is like multiplying it. Basically, that's what we're doing here. And when we're calculating the molar mass of these compounds, we're going to be including the molar mass of the hydrates as well. And just understand, keep this as a mental note. The molar mass of water is about 18.0 grams per mole. We're going to be multiplying this by the number of hydrates present within a compound. So if we're doing it here, for example, we take the molar mass of copper 2 chloride, and then we add the molar mass of water multiplied by 3 because we have 3 hydrates here. We don't multiply the two molar masses together, but we add them to get the total molar mass of that compound. But this is how you write it out. Alright, taking a look at the couple examples we have here. 2.78 grams of iron to sulfate and X hydrate are heated to remove the water, and the mass of iron sulfate ended up being 1.52 grams. So, to find X, which is what we're looking for within this compound, first we need to understand what the mass of the water is. To do this, we take the mass of the entire compound and subtract it by the final mass, the mass of the iron sulfate remaining. This means that the remaining mass is going to be the mass of the hydrate. This gives you 1.26 grams for the hydrate. Just to understand the percent mass of the water within the compound, it is going to be 1.26 grams divided by the whole mass, and this gives you 45.3% of water in the compound. The 45.3% of the compound is composed of water. Now, finding X, to do this, what we need to do is take the masses of the two compounds, take the molar masses of the two, which we can find by looking at the periodic table, finding the molar masses of iron, sulfur, and oxygen, and multiplying oxygen's molar mass by 4, and we get 151.9 grams per mole. Water, again, is 18.0 grams per mole. Finding the moles, it'll give you 0.0101 moles for iron, iron 2 sulfate, and 0.0700 moles for water. Again, we do the ratio, divide both of them by the lowest moles, and we get 1 for iron sulfate and about 7 for water, meaning that X is going to be 7, and the molecular formula is going to be iron sulfate 7 hydrates, or heptahydrate, because the ratio is going to be 7 here. Alright, the final example I have for today is going to be a hydrocarbon that's being combusted. The combustion produces 0.06919 grams of water and 3.338 grams of carbon dioxide. What we're looking for is the empirical formula of said hydrocarbon, because we don't know what the empirical formula is. Since we don't know it, we're going to just have it as CXHY plus oxygen will give you carbon dioxide and water. Now, we know the masses of water, we know the mass of carbon dioxide. In questions like this, and this is just an introduction to stoichiometry, what we're going to have to do is we're going to have to find how many moles of carbon and how many moles of hydrogen are being used within this experiment at the product side. To do this, what we do is we take the mass of carbon dioxide that we already have, 3.338. We take the molar mass, which we can find by looking at the periodic table, and what we do is we divide it to get the number of moles of carbon dioxide. After we get the number of moles of carbon dioxide, which is here, what we do is we multiply it by the number of moles of carbon present in carbon dioxide. To do this, we take a look at carbon dioxide and we see that CO2 has 1 atom of carbon and 2 atoms of oxygen. So we multiply by 1 mole of carbon divided by 1 mole of carbon dioxide because there's only 1 atom of carbon for every atom of carbon dioxide. This is pretty simple, and we get 0.07585 moles of carbon within the compound, within this experiment here. Taking a look at hydrogen, we already know the mass, we know the molar mass of water. We have the mass of water, molar mass of water. We find the moles of water, and what we do is, this is a moles of water. So H2O would cancel out, and we have 2 moles of hydrogen instead of 1 because water has 2 atoms of H instead of 1 compared to carbon dioxide. And carbon dioxide has 1 atom of carbon, water has 2 atoms of hydrogen. Because of this, we multiply the moles by 2 to get 0.07684 moles of hydrogen present. Now, we do the ratio, we compare the two, and we understand that The ratio is going to be 1.00 for carbon as it's a smaller number, and 1.01 for hydrogen, which gives us about 1, which means that the empirical formula is simply going to be CH. This might be a little bit harder to comprehend right now, but we're going to be diving deeper into this the next lecture, looking more at stoichiometry and understanding what goes on behind the scenes as well. And just let me see if I need to explain anything else, but yeah, that looks like that's going to be it for today's lecture. And again, like I said, the next lecture is going to be focused on stoichiometry. If we have time, we will look into yields as well. And yeah, stay tuned. Thanks for listening and watching.